Astronauts use a centrifuge to simulate the acceleration of a rocket launch. The centrifuge takes 30 seconds to speed up from rest to its top speed of 1 rotation every 1.3 seconds. The astronaut is strapped into a seat 6.0 meters from the axis. Part A. What is the astronaut's tangential acceleration during the first 30 seconds? So on the left, I just have a little video of what the kinds of centrifuges that astronauts use look like, just to help us visualize what this problem is asking. And then I also just went ahead and wrote a model that shows more of the conceptual things that will help us solve this problem. So it's good to keep in mind that the tangential acceleration is what changes a particle's speed, and a tangential acceleration only occurs whenever, in circular motion, whenever the particle is speeding up, whereas centripetal acceleration always occurs in circular motion, and the centripetal acceleration changes the particle's direction. So part A is just asking us what the astronaut's tangential acceleration is during the first 30 seconds. And so our knowns for this are just the t equals 30 seconds, the initial angular velocity is going to be 0 inverse seconds, and then we can also easily find the final angular velocity using that 1 rotation every 1.3 seconds info that we were given. And so yeah, we solve for that and we find out that it's going to be 4.83 inverse seconds. So going ahead and solving for the astronaut's tangential acceleration, so we have an equation from this unit that says that the the tangential acceleration is equivalent to the angular acceleration times r. So we know r, but what we need to solve for is going to be that angular acceleration. And so we can use one of the rotational motion equations that we learned from this unit that looks very, very similar to our linear motion equations that we learned earlier in this semester. And I use the angular velocity final equals angular velocity initial plus at, and then went ahead and solved for a, and that a being angular acceleration. And once you plug in our numbers, you end up getting 0.1611 inverse seconds squared for that angular acceleration. So now we're going to need to solve for the tangential acceleration, which is what this problem originally was asking us. And once we do that, we end up getting 0.97 meters per second squared for that tangential acceleration. Okay, part B. How many g's of acceleration does the astronaut experience when the device is rotating at top speed? Each 9.8 meters per second squared of acceleration is 1 g. So this is, part B is actually going to be evaluating uniform circular motion. So it's the astronaut is no longer experiencing tangential acceleration, but they're only experiencing centripetal, which is that acceleration that changes the particle's direction. So we have an equation for the centripetal acceleration. Well, we have several, but the one that will be useful here is going to be the centripetal acceleration equals the radius times angular velocity squared. So that angular velocity that we're going to use for this is going to be the final angular velocity from part A that we solved for. And it's the radius is going to be the same. It's going to be 6.0 meters. And then the problem also gave us, told us that it wanted our units to be g's, and it gave us that 1 g is 9.8 meters per second squared. So using that equation, the centripetal acceleration equals r angular velocity squared, we can plug in our numbers and solve for an angular a centripetal acceleration, my bad, of 139.973 meters per second squared. But now we have to convert it to g's. So once you do that, it ends up being 14.3 g's of acceleration that astronaut experiences when the device is rotating at its top speed. So yeah, that's the end of the problem. Thank you for listening.